Now that we know how to do arithmetic with matrices, it's interesting to look at how those arithmetic operations like scalar multiplication, addition, and multiplication behave with respect to other things we know how to do with matrices, like transpose, or for example, triangular matrices. And the first thing that we have is a theorem, and so this abbreviation right here stands for theorem, and I will actually prove this theorem. So we'll look at the proof in just a moment. But first, let's just think about why it might be true. If A and B are both upper triangular matrices, then so are their sum and product. Well, it has to have something to do with the position of the zeros in the sum and the product, right? So let's look at the proof of this thing. We remember that the definition of an upper triangular matrix is that the entries below the diagonal are all zeros. Okay, so if we look at the sum first, so here's A plus B, then the idea is that if I is greater than J, it should imply that Aij is equal to 0. So I'm just recalling the definition here. I guess I should say, and Bij is equal to 0 because they're both given to be upper triangular matrices. So Aij plus Bij is also going to be equal to 0. And so in picture form, if this is A and this is B, then what I know is that everything under the diagonal is going to be a 0. In each of them. And so if I add these together, then when I look at any entry that's under the diagonal in the sum, like this one right here, well, this is just going to be 0 plus 0, so it has to be equal to 0. Okay, what about the product? So for the product, let's think about the definition. So the ijth entry of the product, so I'm thinking of C as the product of these two things. Cij is equal to the sum as k runs down the length of these guys, aik bkj, like that. So let's see, what does this look like? Well, we'll do the same thing. I'm going to take the a little doodle just to get an idea of what's going on here. And so we've got the here's the upper portion of A, and here's the upper portion of B, and we are multiplying these together to find out what's going on with C. Oh, I missed a line. Okay. Now, in order to see that the product of these two things is upper triangular, what we need to do is check that any entry we have that's below the diagonal is equal to 0. So remember, the condition for being below the diagonal is that the number of rows we've gone down, which is I, is more than the number of columns we've gone across, which is j. So we're looking at where I is bigger than j. Okay, so let's take that and come back to our matrix, our factors here, a and b. So we're going to take I bigger than j. So let's suppose this is the ith row of A, and then we've got the jth column of B, And the key point is that I is further down than j is to the right. So let's look at what happens in the dot product for this entry here. So if we take, actually, you know what? I'm going to make the one from B, I'm going to make it green. Okay, just to make the color coding work out a little better. So from the ith row of A, we're going to have something that looks like 0, 0, dot, 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 dot. And then here at the first time that it meets the diagonal right here, this is the first time we can have a non-zero entry. So that entry there is A sub II. Okay, so this is the ith entry in this vector. And then we're going to have stuff, and who knows, they could be zeros, they could be not, we don't know. There's the rest. Okay, now, meanwhile, what do we have with going on with B? So if we take this, and I'm going to, even though it's a column vector, I'm going to write it as if it's a row vector just to line them up next to each other. Now, in J, we've got stuff, 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 and then the last amount of stuff we have is right here on the diagonal, and this is going to be, since it's on the diagonal, it's going to be in the jth row. So we're going to have stuff, stuff, and we saw that I was bigger than J, so we're going to run out of stuff before we get to the ith position. And then it's going to be like zeros all the way throughout the rest. And so here, this is the last one. This is the jth. And like I said, we're looking at where I is bigger than j. So then when we do the dot product between these two, all of our pairwise products, we're going to be multiplying these things together and then adding up all those things that we get. And if you see, there's going to be a 0 in every single one of them. And as a consequence, we're just going to be adding up a bunch of zeros. And we're going to get a 0. So our entry is going to be a 0. So that's enough to prove that, and that's not really an official formal proof, that's just me doodling out an explanation, but good enough. I think it's a fairly rigorous job. We've guaranteed that if you take two upper triangular matrices and you multiply them together, then you're going to get another upper triangular matrix. So we're done. Signify the end of a proof with a box. Consider it your reward for a job well done. And then we have a corollary. And so a corollary, or corollary if you're British. Corollary is a little simple, easy theorem that you get from some work that you already did without doing any more additional effort, basically. And that is that if A and B are lower triangular, and also of the same size, then so are A plus B and A times B. So in other words, the exact same result holds for lower triangular matrices.